to this video on general theory of relativity, and today in this video we would be looking into something very important, which is called Christoffel symbols, Levi Civita connection, and how these connections helps us to understand more minutely and measure the curvature of space-time. As we all know, the general theory of relativity is all about curvature of space-time, measuring the curvatures and understanding how the vectors and the other things and elements changes. So in this video we would be looking deep into understanding those changes in curvature and how the Christoffel symbols helps us to understand and measure those curvatures. As we know that without curvature there is nothing called general relativity, so this video would be concentrating on measuring the curvatures, understanding mathematics of it, and we will be going ahead to learn what is called Christoffel symbols. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to watch this video. Now in this video I would be doing a little bit of mathematics because Christoffel symbols deal with mathematics. However, I will keep it very simple and I'm going to explain each and every aspect and indices of those Christoffel symbols, which will make you understand and make this video very interesting to watch. So first let us see what are the topics that we are covering. So first we will learn what is Euclidean to non-Euclidean geometry, the shift in terms of understanding and philosophy which happens from the Euclidean space to the non-Euclidean space. What is meant by change of basis vectors? We will first understand also what is a tangent, tangent plane, tangent space, and most importantly what is an affine connection. What is a Levi Civita connection and how does it correct the ordinary derivatives? And most importantly, how does it help to measure the change in the curvature? What are Christoffel symbols? How do we identify the indices and how Christoffel symbols plays an important role in general theory of relativity? So I would request everyone who is watching this video not to skip this video because each and every thing in this video will be intricately related to the basic core understanding of general relativity. So first let us understand what would be that when we move from an Euclidean flat space-time into something like this, which is a curved space-time. First let us understand mentally also that what are the changes that are going to come. Once we understand the changes, then on those changes we will develop the mathematical tools which will help us to understand how the curvature and other things changes. Okay. So we are basically know about Euclidean space, which is more or less flat, and then we move into what is non-Euclidean, which is kind of a curved space, and it has got many other complex manifolds. We deal with surfaces, which primarily deals with the Euclidean space, but now we deal with what is called manifold. Now if you're really wondering about what is a manifold, you can go to my playlist in differential geometry as well as in general theory of relativity, where I have dealt with what is manifold, what is differential manifold, much more in details. We generally deal with Cartesian geometry, but here we deal with what is called differential geometry. And from the Cartesian geometry, we moved into applying calculus. So that is the major change that we do, that we apply calculus to geometry, and the geometry is no more related to Cartesian, but is related to curvature of space-time. So this is, you can say, the first building block of moving from Euclidean to non-Euclidean geometry, and how do we measure them? That is the central part of our video. Okay, so we move from Euclidean to non-Euclidean, we move from flat space to curved space. We also move from an inertial frame of reference, referring to the special theory of relativity, and now we move into non-inertial frame of reference, and the space and time which was different as two identities in Newtonian physics is now lumped up into something which is called a curved space-time. So all these taken together is that we from surface or manifold we move into something which is differentiable, and here we apply the rules of calculus, and the advent of differential geometry comes over here. So the role of differential geometry is very unique, is very important, and if you really want to know more and more about general theory of relativity, the mathematics of it, you need to have a good understanding of differential geometry. You can go to my playlist on differential geometry, and I've made certain videos on the basic fundamental aspects. Okay, so these are the things that which we are mentally prepared, that these are the shifts, these are the changes, and these are the things new which are coming up. And now we see that how we move from the surface to differentiable and apply the rule of calculus. Okay, so now we first come to the first definition of Christoffel symbol. But remember that these definition I would be taking ahead and explaining each and every part. So the first basic definition is that Christoffel symbols represent the connection of coefficients of the Levi Civita connection. Now these are names of different mathematicians called Tullio, Levi and Civita. So don't worry about this. If you don't understand what is Levi Civita, they describe change in basis vectors throughout a given coordinate system. Physically, the Christoffel symbols represent fictitious forces induced by a non-inertial reference frame. Okay, so this is in overall you can say a semi-technical definition of Christoffel symbol. But first, what we are going to take in this definition is what do we mean by change of basis vectors. We will first understand what is the change in basis vectors, because without that we won't understand all those connections. So here comes the first important concept of Christoffel symbols. What is change in basis vectors? If you have watched my earlier videos, I have used a similar kind of an analogy, that if you take a flat space-time and you measure a vector A along this, then we basically draw components of vector along the y, which is called the AY component, and x which is called the AX component. And we draw lines through which we can measure the vector A in a flat space-time with those AY and AX, which are the respective components of the vector A. Now we plot the same vector in a curved space-time which looks something like this, and we mention the x as x prime and y as y prime. Okay, now we draw the same vector A, and we see that the x component of the A vector A prime x is little bit longer, and y prime of the y vector is little bit longer. And when we join these lines, what we find is that A prime x is longer, whereas A prime y is also longer, but the main vector remains the same. That means it is invariant under the certain changes. Okay, so I will go back to this illustration. Now, what you need to understand that when we are measuring the curvature of space-time, which is being done by Christoffel symbols, first we need to understand that the basis of the vectors, how do they change, and what are the essentials that we need to do is that we keep the main vector A as invariant. Okay, so let us say that we have some kind of a curved coordinate systems with x1 and say for example t or something like that, and here are the basis vectors. I'm just given kind of a very simple examples. So you see that if you have already watched my earlier videos, and even if you have not, you have undergone a course in linear algebra, and you know that these two vectors x and y can be joined with a dot product, which is called u dot v. So the basis vector, as you see, t in the t direction and basis vector x in the y direction, whereas we cannot use a simple dot product just to mention that u dot v equals to the first component of u with the first component of v plus the second component of u with the second component of v. It is not possible. I mean to say, when we move into a curved space-time, when we see that the basis vectors are changing. So what we do is that we use this, right? This is G is something which is called the metric tensor. It acts as a kind of a coefficient which serves that in case that we are unable to use the dot product, this G term actually serves as a correction to measure the causal structure of space-time. Again, if you want to know more and more about metric tensor, I have a separate video on that. But for this particular video, let us understand that in a curved space-time, the dot product generally never works, and you use a special metric which is called the metric tensor G in order to do the measurements correct. Okay, here you see that let us have some curved coordinates with coordinate axis x1 and x2. Now these could be x and y. For example, just note that the coordinate axis does not necessarily have to be perpendicular to each other, because this is a curved coordinate. And the basis vectors in these directions are labeled as e1 and e2, right? Okay, now imagine that you move along the x1 axis and see how the vector changes, the vector e2 changes along this x1 axis. So a small change in a vector along the coordinate axis is simply the partial derivative with respect to the particular coordinate, which is given by this. So to avoid cluttering, I have just drop the idea of mentioning the vector signs or the arrows. So this derivative, which is this red vector, it can be divided into its components along the x1 and the x2 axis. So what I'm trying to make a point over here is that as you see that the basis vectors are moving and they're changing. So what happens is that this small change in vector along the coordinate axis is simply the partial derivative with respect to that particular coordinate. So this is given by this. Okay. So here comes the first concept, first understanding that Christoffel symbols tell you how the basis vectors are changing. If you have seen just a few minutes earlier, I have shown you that the basis vectors really change from one place to another, and here is this derivative vector, which is this del E2 by del x1. This is the derivative vector, and this is what Christoffel symbol does. It tells you how the basis vectors change. Okay. Now, before we go deep into understanding what is a Christoffel symbol, we need to have a basic idea of what is an affine connection. Now, in order to again define what is an affine connection, I would take a step back, and first I would say what is basically a normal tangent. Now, as you know that in geometry, the tangent line, or simply a tangent to a plane curve at a given point, is a straight line that just touches the curve at that point, right? So important is that it just touches the curve at that point. Leibniz defined it as the line through a pair of infinitely closed points of the curve. Now, as the line passes through the point where the tangent line and the curve meet, it is generally called tangency. The tangent line is going in the same direction as the curve and is thus the best straight line approximation to the curve at that point. So this is the best straight line approximation to the curve at point. So this is generally what is called a normal tangent. Now we will take one step ahead and we will try to define so it comes from the Latin word tangere, means touch. So we will take one step ahead and we will try to understand what is a tangent plane. So a tangent plane to a surface at a given point is a plane that just touches the surface at that point, right? So here it just touches the curve at that point. Here it just touches the surface at that point, right? So, and here this one, this red one, this is called a tangent space. What is a tangent space? A tangent space of a manifold, because we are now generalizing, so we have to inculcate the concept of manifold. Tangent space of a manifold generalizes to higher dimensions the notion of tangent planes to surfaces in 3 dimensions and tangent lines to curves in 2 dimensions. In the context of physics, the tangent space to a manifold at a point can be viewed as the space of possible velocities for a particle moving on a manifold. So just to tell you easily that from tangent line we move to what is called a tangent plane. So it is a plane that just touches the surface at that point, and tangent space is something which generalizes the higher dimensions, the notion of tangent plane to the surface. But here is something very important I would like to make a note, is that remember, tangent plane is a geometric object and tangent space is a vector space of a linear functional, and it is more or less abstract, right? So this is very important before we go into affine connection. Now we will define what is an affine connection. Now you see this is a sphere and these are the 2 tangent space. This is a tangent space, this is a tangent space. So on any manifold, an affine connection is a geometric object on a smooth manifold which connects nearby tangent spaces. Again I repeat, it connects nearby tangent spaces as shown on the left hand side figure, those 2 tangent spaces. So it permits tangent vector fields to be differentiated as if they were functions on the manifold with values in a fixed vector space. That means a tangent space will have numerous tangent vector fields and it will connect the nearby tangent spaces so that we get a function and we can do better mathematics with that function. Okay, so here is my demonstration. Let us assume this M to be a kind of a manifold, a smooth manifold to be technical. These are the tangent spaces, right? And here you see one tangent space P prime, so it connects the nearby tangent spaces, these 2 lines. Again you see R and R prime, these are again connecting. So this connects to this connects to this. So what I'm trying to say you is that on any manifold, smooth manifold of positive dimension, there are infinitely many affine connections. So if the manifold is further endowed with a metric tensor, which we will see, then there is a natural choice of an affine connection called the Levi Civita connection. Okay, so why now you see that why we first learned about a tangent line, a tangent plane, a tangent space, and this tangent space actually defines what is an affine connection. So again, an affine connection is an object on a smooth manifold which are connecting nearby tangent spaces. Now hold on, you might be thinking that why we are dealing with affine connection, because now you understand in general theory of relativity everything is a curvature. Now once we want to understand a curvature, we have to have tangent spaces. Now until we have a geometric definition or mathematical tool that we can connect the nearby tangent spaces with a function, then how we can measure the movement or curvature of space-time. So that is why we need something which is called an affine connection. Okay, so the affine connection has its root in 19th century by these two people. It was not developed until early 1920 when Levi Civita, as a part of his general theory of connections, and Hermann Weyl, who used the notion as a part of the foundations of general relativity. The terminology is due to Levi Civita and its origin in the identification of tangent spaces in Euclidean or by translation. So what happened is that a choice of affine connection makes a manifold look infinitesimally like Euclidean space. This is central. This is very important. Now, anything which is very similar to a Euclidean space, it becomes easy to do the geometry. It becomes easy to do the mathematics. It becomes easy to apply calculus. So, these two gentlemen, I mean to say, Hermann Weyl actually, coined the term which was later developed by Levi Civita. So they actually coined the term which is affine connection. Why? Because we want to define something which would look infinitesimally like Euclidean space. So from tangent plane we go to tangent space, and from tangent space we go to affine connection. So if we get anything on Rn, the idea is that that a choice of affine connection makes a manifold look like infinitesimally like Euclidean space, and it helps us to solve the problem. So I think that at this point, while we are moving into Christoffel symbols, why affine connection is important, because without an affine connection, we won't be able to connect the similar or the nearby local tangent spaces. Okay. So I would like to take a one-by-one step ahead. So we know what is a Riemannian manifold. So this is a manifold which is particular to differential geometry and mostly to general relativity. Each manifold is characterized by metric tensor, step number 1, which is given by G mu nu. These type of manifolds which have a metric tensor are called Riemannian manifolds. Now these manifolds also have an affine connection. Now the question is that why will they have affine connection? Because these are manifolds. So obviously these manifolds will have tangent spaces like this. Tangent spaces P and pre pi, and in order to define those tangent spaces we need an affine connection. So these Riemannian manifolds have an affine connection, and these affine connections are connected with Levi Civita connection. So the Levi Civita connection is a special case of an affine connection which has got a manifold with a metric. Now as we will see in the later second and third part of the video, that Levi Civita connection has not only got the metric as a not only has got metric tensor, it has got Schwarzschild metric, it has got Kerr-Newman metric, it has got spherical, so it has got different kinds of metric. But let us understand that from Riemannian manifold it has got a metric tensor G mu nu. It has got an affine connection because these affine connections are connected to tangent spaces. We need tangent spaces in order to define how the nearby points are being located. These are connected to what is called a Levi Civita connection, and an affine connection for a manifold with a metric is known as Levi Civita connection. However, this Levi Civita connection is technically called a covariant derivative. Don't worry if you don't understand what is a covariant derivative. You can just understand that in curved manifold ordinary derivatives do not work. So we need something which is this inverted triangle, which is called the nabla sign, and this covariant derivative actually helps to correct the ordinary derivatives because it really doesn't work here. And only thing is that remember that Levi Civita connection has to be a torsion free connection. We are not taking torsion free right in this video. I will develop the next video where I will show you how this torsion free is one of the features of Levi Civita connection. Okay, let us take turn our page and write it something on a fresh manner. Yes, the question is that what it has to do with Christoffel symbols. I mean to say, we are all understanding tangent spaces, etc. But what it has to do with Christoffel symbols? Okay, so let us write it fresh. We have a Riemannian manifold which is endowed with a metric tensor G mu. It has got an affine connection, something like P prime, which connects the nearby spaces. These are the affine connection has got something which is called a Levi Civita connection. So affine connection for a manifold with a metric is a Levi Civita connection. It is torsion free and it has got a covariant derivative. And remember, in a curved manifold, because ordinary derivative doesn't work, we need a covariant derivative. Now here comes the main important part, that Levi Civita connection expresses through a set of connection coefficients, or as they are called, Christoffel symbols. That means we need a connection, we need a coefficient through which these connections or those corrections will be done. So that is what Christoffel symbol is all about. It is nothing but the Levi Civita connection expressed through a connection coefficients which are called Christoffel symbols. A few illustrations will make things much more clearer. Okay, so you see here that because the ordinary derivatives cannot work here, right? So as the basis vector also changes, hence Levi Civita comes to save the necessary corrections to ordinary derivative. So this is important. So as you can specify a certain coordinate system on the manifold, the Levi Civita or the covariant derivative can be completely expressed as a connection coefficient. This is how it looks like. We will come to this part later. Don't worry about those symbols. This is what the Levi Civita connection is, and it connects nearby tangent spaces by introducing a correction notion. That means something is wrong and this coefficient is correcting that. This one is called basically the ordinary derivative. You can understand because we are just using the partial derivative. So this is the ordinary derivative in Cartesian coordinate, and this is the correction term or the connection coefficient, which is the Christoffel symbol denoted by the Greek letter capital gamma, which corrects the ordinary derivative for an arbitrary curved manifold. Clear? I hope this is clear. So we get the Levi Civita connection which connects the tangent spaces. Why we need to connect the tangent spaces? Because these are manifold and these will have tangent spaces, which is a generalized form of tangent bundles, and here we get the corrected notion. The ordinary derivative is already there because it follows the partial derivative in the ordinary Cartesian coordinates plus the capital gamma term, which is the correction term of the coefficient, which is the Christoffel symbol. Okay, now we got a kind of a mathematical understanding of geometry of Christoffel symbols, that it does the correction when the basis of the vector changes, etc. But what about the geometric meaning of Christoffel symbols? I mean to say, how does it really look like? So we can find it something like this. So this is from my previous slide, which you have seen, that it doesn't obey the dot product and we have to use the metric tensor M. Okay, this is the change of basis vectors. Now you see here, I've just written in plain language that Christoffel symbols can be interpreted as describing how basis vectors change through a given coordinate system. So a nice way or an intuitive way about this correction coefficient is to think of them as a correction to an ordinary derivative, right? Resulting from the fact that you may have a curved manifold or coordinate system. Now geometrically, here it comes, the basis vectors may change due to the coordinate system being curvilinear or due to the geometry of space itself being curved, and the Christoffel symbols describe both of these. So what I can say is that geometrically Christoffel symbols can be interpreted as describing how basis vectors change throughout a given coordinate system. The basis vectors may change due to the coordinate system being curvilinear or due to the geometry of the space itself being curved, and the Christoffel symbols describe both of this. So here in the box I have written the Christoffel symbol are essentially defined as the derivative of basis vectors. So when we do the derivatives, we get another vector, and these are the derivative of those vectors. Okay, so from this definition, you see why the Christoffel symbols are coordinate dependent. So they are obviously dependent on a coordinate, right? So here you see this is how it looks like. Now this particular part shows how the how much the basis vectors E mu changes along the x nu coordinate. So I've just given here you see G mu nu equals to E mu dot E nu. Here we can use the dot product. Why? Because there is a metric tensor G. And this one shows how much this derivative and the E lambda actually overlaps. And remember that they are coordinate dependent, and we will obviously justify, and we will see that Christoffel symbols are not tensors, right? So what happens from here is that it means they are actually not tensors. There is actually a nice visual way to see the Christoffel symbol. As you see here, the components are being present. Okay, so this one says how much the basis vector changes, and the dot says how much the derivative of the E lambda overlaps. Now, if you're really wondering that why do I mean by overlapping in the dot product, you can go back to my playlist in linear algebra, and you can see there's a video called dot product, cross product, inner product, outer product. And I have visually demonstrated through geometry that what do I mean by overlapping. Okay. Now let us say that we have a curved coordinate system with the coordinate axes x1 and x2 with the basis vectors labeled as these are the lines, so E1 and E2. Now imagine you move along the x1 axis and see how the E2 vector changes. So again, a small change in vector along it is simply the derivative. So here it is, and we see this is the derivative. Now remember, I also always avoided the cluttering, so there is no arrow. This derivative vector is now divided into its various components like x1 and x2. Okay, so we take and we zoom this vector and we connect it with this red vector, right? So what we do is that this is taking the dot product of this red vector with different basis vectors. So here we see, you see this one, right? And now we put an arrow, yeah. So you see that del E2 and del x1 is basically what we have done is we have taken the dot product of this red vector with the different basis vector, one with E1 and this one with E2, right? So we have taken the dot product of this red vector with two different basis vectors, E1 and E2. So this is in rough sense what the component of Christoffel symbols look like. Don't worry about those indices, we will explain it later. In other words, so here it comes. So in other words, what we can say is that this one E1 and E2, and then gamma 1 on the top 2 1 and gamma 2 T2. So what we can say that Christoffel symbols geometrically represent different components of the derivative of basis vectors. So we've taken the derivative. Now these basis vectors E1 and E2 we are geometrically representing. Another way to say is that if you were to take the derivative of a basis vector, that is how the vector changes along the same coordinate, this would give you another vector, and the Christoffel symbols then represent the different components of this vector. Okay, so it is quite simple. Now what we would do is that we will take this equation and we will see how we can write it. I'm going to see what those symbols and how do we write it about. Okay, so you see here and this one, and we get this one, the red one, and here we see Christoffel symbols geometrically represent different components of the derivative of basis vectors. And if you are to take the derivative of the basic, which this is what I was just telling, it would give another vector. The Christoffel symbol then represent the different components of this new vector, and it is a correction to an ordinary derivative. So this I have explained earlier that the ordinary derivative really doesn't work. So what we need is basically a kind of a what we call the derivative, this vector, the Christoffel symbols. So that is how it is. It is basically a correction to the ordinary derivative. Okay, so let us write it in a clean fashion. So we got these two, right? Del E2 by del x1, del E2 by del x1, and E1 and E2, right? So what we do, we will take first this gamma term, which is the Christoffel symbol. And here you see this will be written as this. Gamma followed by, on the top we will write lambda followed by mu nu. And this one will be represented as something like this. E dot del nu at the lower end and E mu at the lower end. So what we will do now is that I am going to multiply E lambda on both of the sides, and what we get is this one. Okay, don't worry, I will just explain you what are those things all about. So what I have done is that I have taken the 1 to 1 of the Christoffel symbol gamma term and written in terms of indices. Why? Let the suspense be on. I will soon explain to you. Second part is that I have taken this term E dot and I have taken this partial derivative, multiplied it with E lambda, and what we get is this. So this is a compact way of writing Christoffel symbols, but obviously you have a question that how does it relate to general relativity? We understand indices, up, down, everything, all those gymnastics are there. But how does it relate to general relativity? Okay. So we know that in general theory of relativity, we are dealing with four-dimensional space-time, right? Three-dimensional XYZ space and a one-dimensional time. Now, so we need to write the indices so that we can measure those changes in space-time from 0 to 3. Okay, so here we write step by step. Okay, so here we got this del V part. We know it is. Now we will take this one, the Christoffel symbol. So you see that the first step is that we need to write it in indices, which will go from 0 to 3. So first we write 0. That means this lambda from here, it will go up to 0. And then from 0, it will go up to 1 and so on. Right? So this is that is why we use Christoffel symbol lambda. And that is why we use 0 and 1. Okay, done. Now we go for this lower indices part, that is E lambda. Right? So what it does, it again changes to 0. And what it does, it again changes to 1. So now you see that these indices will fly through. So that is why we are using these terms. So we can write this del V E mu equals to the first term, which goes from E0 to 0. The second term goes from E1 to 1. And the third term, which goes from E2, 2 to 2. Okay, let us write it quickly in a cleaner way. So this one will range from 0 to 3. This one will also range from 0 to 3. And this will be equal to 0, 0 plus 1, 1 plus 2, 2 plus 3. And now you can imagine that these are basically nothing but the changes of basis vectors along the four-dimensional space-time, which is Einstein's general theory of relativity. Right? So the Christoffel symbols indeed represent different components of a vector, this one, and Christoffel symbol represent how the basis vectors change through a given Riemannian manifold, which is the heart of general relativity, because the entire general relativity is revolving around what is called a Riemannian manifold. If you want to know more about Riemannian manifold, you can go to the first, I think the second video on the mathematics of fundamental concepts of general relativity I have explained over there. So far what we have understood what is the Christoffel symbol, why the indices are there, and why we mention those indices, what are Levi Civita connection, and what are affine connection, and how does it come from. So here it is, and we can also mention one thing, that this is something which is related to a fictitious force, which is gravity. It can be expressed in terms of metric tense and other metric. It has got a first kind Christoffel symbol and a second kind, and it has got a torsion-free property, which we are going to take up in the next video, because unnecessarily it would be too long. So these are the things we are going to cover one by one. How Christoffel symbols represent gravity, what are the other metrics in which it can be expressed, what is the first and the second kind of Christoffel symbol, and what is the torsion-free property, right? So let us put it in simple language till now what we have learned. So we moved from flat space to curved space. We saw the change in the basis vectors. The usual dot product does not work, so we use metric tensor. When the basis of the changes, the ordinary derivatives do not work. So we use a correction term, which is via Levi Civita connection. The Christoffel symbols is the correction term coefficient for the ordinary derivative, and the indices varies from 0 to 3 as it signifies the four-dimensional space of general relativity. So here is a quick summary. We learned from Euclidean to non-Euclidean. We've learned from flat space to curved space. We learned from how the basis vector changes, tangent plane, tangent space, and affine connection. Why affine connection is important, what is a correction term, Levi Civita connection, Christoffel symbols in general theory of relativity. But remember, this is not done yet, because the Christoffel symbol has got certain other significance, certain more important details which needs to be formulated, and I will be making up slowly in one by one in other videos. So that's it for today's video. Please put up your comment. Please subscribe to my channel Physics for Students. Click on the bell icon and click on all to get all the notification from Physics for Students. I will be waiting for your comment on this Christoffel symbol first video, so that we can carry on with the second, third until we are done and complete with what is Christoffel symbols in general theory of relativity. Thank you for watching this video. Stay tuned. I'm coming up with more interesting videos on physics, mathematics, and other areas of science. Thank you very much. Stay tuned to watch more. Till then, goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.